Hello everyone, welcome to the 5th episode of FPGA Limerick. In this episode, we will take a close look at the Hello World example for SpinalHDL. And based on that, we will also demonstrate the basic design flow for SpinalHDL. By the way, the script of this episode has already been posted online at fpga.postring.com. Yeah, this is our companion blog, fpga.postring.com. As mentioned in the previous episode, our GitHub repo can be checked out from this tag, but this time I will do it through Tortoise Git instead of command line, just to show a different way to do the checkout. Please use this tag. 1.1.4 tag. Okay. Now let's take a close look at the folder structure. First, I think the scripts folder has all the useful scripts. You can find the details of them. I think in the README. If you go to our GitHub repo, in the README, you will find the explanation for those scripts. I think this script is pretty useful for you to create a new project. Basically, it will copy all the things from the Hello World and use Hello World as a template to create a new project folder. And the other two, I think we already mentioned earlier. This is for the setup of the WSL, the Windows Linux subsystem for Linux, and please use Ubuntu 20.04 for that. And this is the one to set up the MAC address for dummy address for if you use a fixed seat license, as the MAC address for WSL is randomly generated, so you might need that to match the MAC address with your fixed seat license file. So okay, so go back to the slides. I think at the top for the Hello World itself, at the top level, for the Hello World at the top level, we have this SBT file, and we also have those three additional files for the lint and the format, which we mentioned in the previous episode. And this project folder contains additional files to set up the SBT. For example, this one is to set up the plugins for the lint and for the format. And also this one is to set up the version of the SBT. We will use 1.8.2 version for SBT. And here is the source folder. I think most of the SpinalHDL code for design, they should be put under this folder. And the main folder actually contains a log4j2 configuration file, which also mentioned earlier. This is for the logging configuration. It has to be put there. I think this is just the convention for the log4j to find their configuration. And this is the test folder we use for test bench. All the SpinalHDL test bench, please go and put them into this folder. And the CocoaTB is a different tool. It uses Python to create test bench, which we will mention that and in later episodes. It's a different tool to create test bench, and we will discuss that in later episodes with more details. So that's pretty much all the folder structure. And okay, so let's take a look. First, I think since I mentioned the scripts, I just want to show that very quickly. Let's see. Let me open. Okay, let's see. Just open WSL, because the shell script, I think it has to be run under WSL. Okay, let's make ourselves root. Then let's go to, for example, if we want to create another project called ABC, what I can do is make ABC in this folder here. Then okay, it copied this ABC folder. See, it has similar folder structure, or the I should say this. Okay, so it has all the files at the top level, and also the source and the project test folder structure. Okay, so let's go to the hello world. Yeah, okay. Now let's take a look at the design flow for SpinalHDL. So the design flow for SpinalHDL is basically just like Verilog. You first prepare all the parameters and set up the source code, feed the parameter to the source code, and then there is something called a spinal config, which is another set of parameter just for the configuration itself. It will take the source code and it then produce the Verilog or system Verilog or VHDL, depends on what you choose. So let's take a look at a hello world example, and then we will show you how it was generated. First, let's do that. Let's open it with our edit. Okay, the file is opened with our IntelliJ edit. Okay. Okay. Oh, I think I mentioned this in the previous episode. We need to set something up for the first time. Okay, this is correct. In the setting, I think first the build system, to make sure you have GIE, yeah, and also in the editor part, make sure you have the format is still scalar format, and in the inspection part. Okay, you need to create that. Okay. Just assign it as this should be a test source root. Okay. Yeah, now the lint will look into this folder. Okay, and also we can open the SPT terminal. Okay, now since we mentioned the design flow, I think if we just want to generate the code, what we can do is we can do run, for example, to get the source code. We can choose one, but here, since we mentioned the parameters, if you look at it, the source code, which is here, the source code actually runs like this. It takes two parameters and has some default parameters. So if we do things like this, we are taking the default parameters, which is base clock is 100 mega, and the output clock is 24 mega. But we can also choose a different way to set up the parameters. For example, here he is running actually this package. So what we can do is, and we can set this is the base clock. Maybe the instead of generating a 24 mega, we can do a 10 mega. Okay, now it generates the files, I think, in both Verilog and the system and the VHDL, since we choose Verilog and the VHDL. And I think in the folder, in the Hello World folder, we choose I think now it has a gem folder, which has the one we just produced. Please look at this is what it does, because I think we choose 100 mega and 10 mega, so this is adding 9 and 1 for the counter. Now if we do that differently, we say we want to do, instead of 10 we do 20, for example, 20 mega. Okay, now the Verilog file generated has also been altered. It become adding 4 and 1 for the counter, and the counter value we will just explain soon. So basically, this is how it was generated, and the design flow is we will have the whole file, and we have the parameters here, and the parameters will be set up when we do the generation of the Verilog code or VHDL code, and it was set up here. And then there is another configuration we will use for setting the clock, how to set up the clock, how to set up the reset, which we will mention and soon. So this is how it would run, and it fits the flow I just mentioned. Now let's take a look at the code itself. But before we take a look at the code, I want to give an explanation of basically the background of this Hello World example. The Hello World example actually is NCO Counter. The NCO stands for numerically controlled oscillate. Basically, all we need to do is, like, say we have a base clock, and we want to generate an output clock based on this base clock. And this is very common in like any digital design where we want to we have especially in the FPGA, usually there is only one main clock, and everything else is based on that clock. So in that case, the base clock is fixed, and the output frequency is predefined. So they want to do a counter so that we will generate the output clock. Basically, it's not a clock technically, it's a enable pause, because in FPGA design, actually, as I said, we usually use one base clock, and everything else is just enable pause. So for us to do that, we need to figure out the GCD of the base clock and the output clock, and then we simply divide them with the GCD to simplify the clock frequency to get a simplified fractional, and then say it's n over m. Then we basically is just for the counter, we just add every time, for every base clock frequency, we just add an n and modulate that by m. So if every time if the counter rolls over, we just generate a clock. So that's very straightforward. Okay, now let's look at the code. So here's our code. I think usually the code can be divided into several subsections. The first is you have something called a package. Usually it's like we can follow the Java naming convention. The package should be a reverse order of some URL. So I just happen to found this name is very convenient, and it's just the reverse URL for our companion blog. But you are free to choose any name you like. You don't have to follow this reverse URL because some in our design, for example, there is some other code that we use in the common package, which you will see, like the common package. They just use the package name as common. For example, the common package, if you open it, see this is the package common for that. So but usually you can choose if you can find a reverse order name that will just follow the Java convention. So this is the package name we use. And then the second part is the import, which kind of like includes in C++ or in Verilog. And those are the package we will reference. And by the way, if you say you import something that is unused, for example, spinal, or maybe just say spinal, let's see, call, and is that okay? Sim maybe. Okay. And if you do that, and then if you do a scalar fix check, it will just tell you that, okay, so this is unused input. You can just, I think, fix it automatically if you just say scalar fix. Okay, it would, okay, so like it still tell you a warning, you just remove it. Okay, yeah, I think the scalar fix will, okay, let's do this. I think the scalar fix will fix that for you automatically. Okay, found that. And then I think on the file system, it should okay, it didn't fix it, okay, for whatever reason. Yeah, you just remove it. Okay, so the scalar fix will try to find you if you use some unused import, it will flag it. And so this is like the include part for our code. I think you, especially this one, is a necessary part. You need to do that. And this is the log part. We need this for our log, and those are the common things we will, especially the here, the main config. Actually, this comes from the common package. If we look at that, let's take, how do I, oh, okay, go to implementation. Yeah, this is our main config. It was in the common package. Okay, so go back to the code. So, and this is import. The third part is the case. Please write things like this. I think use the case class instead of the regular like non-case class. I think the reason is that the case class, if you use the case class, you don't need to do the new, and also case class is recommended by the SpinalHDL code convention. I think we mentioned that earlier. In the SpinalHDL code convention, it was specified that here's the SpinalHDL code convention. It says class vs case class is recommended to use the case class. You can find all the detailed reasons here. Okay, so please use case class and extend that from the component. And this is like similar to the module, like the module of the VHDL, also of the Verilog. Okay, or the module of the Verilog or the entity of the VHDL. So this is the name, module name, and this is the parameters. I always start with a G and the score. This is just for like what the style I like, because it's a reminiscent of the VHDL, where the G stands for generics, which is the parameters in Verilog. Anyway, this is the parameters for the module, and then the next is basically the port list. The counterpart in Verilog is the port list, and here please write things like this. Always do a bundle and then called IO, and then here you can specify with input or output. If it's registered, yeah, you can specify register with the initial value on it, so it become a register with initial value. And here's the interesting part. You see, we mentioned in the slides we're gonna figure out M and N, and then use the M and N, we can figure out the width of the counter. But see here, we do it very, I would say, elegantly, because see this function, if you do that, this comes from our common package. So in our common package, utility object, this function, all it does is it just simplify the ratio, found the GCD and simplified the ratio, and this all done easily since we are using Scala as our base language, and the Scala has its high level programming language, so it supports GCD directly, and so we can do that in just a few lines to figure this out. If we do that in Verilog, I don't think Verilog's system function will support the GCD directly. So for us to do that, we have to jump through a lot of hoops to get the GCD. Even if we can accomplish that, I believe the code will be very bulky and messy. So that's, I think, is the benefit of using SpinalHDL, because high level programming language, and then with that we can just use one line to figure out the simplified and M, then set up the width correctly based on that. Okay, so the next one is no IO prefix. Usually we will put this. Now look at the code generated, the code we just generated. See the IO will keep the name as the same name as we specified. Those two are implied, so they wouldn't show up in our SpinalHDL file, but they will show up in the final Verilog file. And since every design needs clock and reset, so that's why it's all implied. They are specified by the config instead of the design port list itself. Now let's take a look. If we remove this line, if we don't do this, what will happen? So if we do the okay, you will see now this time the name will be different. There's a prefix called IO because we use the IO as our bundle name, so it will just append the IO, prepend the IO in front of those signal names, so it becomes like this. But sometimes we don't like that, that's why we say this now IO prefix. And then then yeah, the name the signal name will just keep it as is. Okay, so the next part is our main body, which we will discuss later when we discuss probably in the future episodes. We will discuss the Verilog versus SpinalHDL and how we transfer from Verilog to SpinalHDL. But for now, let's just say this is the main body, and here I think this is the NCO register we created. Basically, it's the counter, and then this is the counter value will be output to this, and this is basically equivalent to the like always in Verilog, but it will be done in a more concise fashion. See, we have a synchronous reset, and then here's the counter. See, the counter, it just follows the rule we just mentioned. There is an equation, I think, in the slides. We say, okay, so this is like the counter. We have the n and m. It's just the counter plus n modulo m. But in implementation, we just, if it rolls over, we add this value. Otherwise, we just add n and minus m. Otherwise, we just add n if it's not overflow. And then every time when it overflows, we will generate a pause. So supposedly the pause will be equal to our output clock frequency. So okay, so that's that as a hello world. That's pretty much it for the main body. And then can come the next part. See, we have create an object with the same name as the class. In Scala, this is called a companion object, and in that here we also extended the logging in order to do the logging. Otherwise, you can just do it without the extents. And then the object contains a main function. Inside the main function, the key part is we need to generate the clock, the Verilog or VHDL file. Now we specified the parameters or the generics here based on the command line input, but we also use something called main config. And this main config, I think, which I just showed you, it was here. It was derived from this spinal config. We just specify something our own. For example, we say the target directory is gen. That's why you see this gen folder here. It's called a gen because we said it's the name is gen, and also we said that the clock is in rising edge, and the reset is asynchronous, and it's active low. That's why you see the name is like reset is active low. It's just async reset. Okay, and actually there are more things we can do to the spinal HDL config, if you again go to the implementation, you will find the full list of the things, the parameters you can tune for the spinal config. I will leave you to explore this. Some of them are related to the VHDL, but some are just applied to all the languages. So so we can take a look. But usually the one that we are interested in usually are already specified in the main. But you feel free to you should feel free to create your own config, and if you like. If there's something design is different than this. So okay, so that is pretty much the things we have we need to generate the VHDL file. Let's take a look at our slides. See if there's anything left. Okay, we mentioned the background of the hello world and the code structure and the configuration. This is something I just showed you. Okay, thank you. And actually, to summarize, I think from example we will see that the benefit of using SpinalHDL is we can leverage on its on the scalar and on its high level programming language side, which will make our code very concise and efficient. Otherwise, if you do a low level Verilog design, the code will be bulky and messy. So that's the beauty of SpinalHDL, as demonstrated by this hello world example. So that's that for today. So we just showed you the design flow of the SpinalHDL, and I think next episode we will show you the simulation flow of the SpinalHDL. Actually, we can simulate the SpinalHDL itself in Verilate. Or later, I will also show you how to do that in CocoaTV. So that will be the next few episodes for simulation. But for design flow, I think it's just a very straightforward. Get the parameters, write the code, and then generate them through the configuration. Okay, I think that's all for today. Thank you so much for watching, and please subscribe this channel if you feel this is useful to you. Thanks again, and bye bye.